Okay. Uh, Today we are going to start with reflection, what we have learned last week, and then we are going to discuss about the advanced adders. And if you have time, we will go for the binary multiplication. There are three algorithms that we would like to discuss in this chapter. And last week, we forgot to have the presentation of the assignment number 2, right? So maybe after the break, we will have the presentation on assignment 2. There are 4 of you will do the presentation, right? So please share your answer to the class. And maybe it's better if you can share with your Webex, okay, on your Webex, so that everyone can see your possible solution. Anything before we start? Any questions or any comments? Okay, reflection. What did we learn last week? What did we discuss? Adder. Okay, we discussed about adder. And what else? What the adder that we have discussed? We discussed about liberal adder. This is a special kind of adders. There are so many kinds of adders. And the liberal adder is the very simple one. And we can start from 1-bit adder. And in the lab, we implemented the 4-bit adders. And some of you might be successfully test it, or maybe not still working on it. What else that we discussed last week? Only adder? And that's it? Number system. We talk about number system, right? There are so many number system, but we talk only 2 types of number system, which are sign magnitude and the 2 complement, right? In sign and magnitude, it can be signed and unsigned numbers. They can be signed and unsigned numbers. And we're also talking about the sign extension. What is the sign extension? For example, if you have a small number of bits of data, and if you would like to extend it to the bigger one, let's say from 16-bit to 32-bit number, you can do design extension. What does it mean, design extension? If you have, let's say, only 4-bit like this, and if you would like to extend it into 8-bit, we have to look at the side bit. In the 2 complement system, we have the leftmost bit as the MSB, or the most significant bit. So we just duplicate the MSB, Let's say if we would like to have the 8-bit, we will do something like this. And this is the sign extension. Okay. Anything else? Or that's all that we discussed last week? Okay, that is really fine. I would like you to do something like this in every subject before starting the new topic. It is better to recall what you have learned last week. Okay, so that when we talk the new topic today, so that you can follow up. But today you cannot realize or you cannot recall what we have discussed previously. Try by yourself to follow up the topics that we just discussed. Today we are going to have the discussion on the very advanced addition. This is one of the example of how to implement the better circuit, because in chapter 1 we talk about how to make the computer faster. We can do something like we can apply the more frequency to the circuit. For example, we use the faster CPU. But by using the more frequency, we put more frequency to the CPU, and we hope that the CPU can run faster with the same circuit. But today we are going to discuss what happens if we make the circuit better. How can we make the adder faster with the same clock, with the same speed, okay, with the same frequency? Let's look at the simple analysis here. In case that we have a 16-bit ripple adder, we can define the delay as the amount of time that the signal passes through the logic gate from the input through the output. How long that we can get the output after we apply the input to the system. In the lab, we do the functional simulation. But this week, we are going to tomorrow, we are going to apply the timing analysis to our circuit so that you can see what the delay is. And today, the definition of the delay is here. It's the time that the circuit get the input signal and then it produces the correct output. The question is, what is the delay or the critical path of the ripple adder? In ripple adder, you can notice that last week we have something like this. We have 3 AND gates, and then the output of the AND gate were fed to the OR gate as the input, and we have the output like this. This is the Cout. And we have something like this for result. This is a very simple circuit that we discussed last week. We have something like this. And we create a box. And we duplicate this box many times, as many as we want. For example, if we want 4 bits, we duplicate this box 4 times. If we want 16 bits adder, we duplicate this box 16 times. And we feed the Cout of the very first bit to the next bit. For example, the Cout of bit 0 will be fed to Cin of C of bit number 1, and so on. But how about R? R is independent from C out, right? R is independent, but C out here depends on the previous bit, the previous C out. So what is the critical part of the Lippo adder if we have, let's say, 16-bit adder? The critical part is the part that takes the most time in the circuit to get the list mode. Let's say if we have something like this, we have a C in, we have A0, B0, and here is C1, and this is A1, B1, this C2, A2, B2, this is C3, A3, B3, and here is C4, in case that we have 4-bit. But if we have 16-bit, if we're using the 16-bit adder, this series will continue until C16. The circuit will continue like this until C16. Right? So the question is, what is the critical part of this kind of Lippo adder? We can look at the equation, and you can see what is the critical part of this kind of circuit. Look at the analysis here. We have C1 as B0 and C0, or A0 and C0, or A0 and B0. We have this kind of equations. And until C16, we have something like this. What does it mean? It means that in C16, we have to wait for the value of C15. How about C15? C15 just look like this. B14 and C14, or A14 and C14, or A14 and B14. And in this equation, what does it tell us? C15 has to wait for C14, right, to get the correct result. And again, C14 has to wait for C13. C13 has to wait for C12, and so on. It means that C16 have to wait all the way until we get C15, right? And this is the critical part of the Lippo adder. Because this bit, this result, has to wait for this one has to wait for C14, the C14 has to wait for C13, and so on. Assume that if we have the gate delay for AND gate and OR gate the same amount, but in practice, you know that maybe AND gate is a bit faster than OR gate. You may notice that, but in this simple analysis, we assume that the AND gate and OR gate has the same amount of gate delay for simplicity. So in 1-bit adder, we have 2-level AND OR. This is the circuit. Why we say that it's a 2-level AND OR? go back to the circuit like this. This is the circuit that we discussed here. It's just like this. You see that in the first level here, we have AND gate. And the second level, we have OR gate. In hardware, all the devices here in the same level, they work at the same time. What does it mean? All three AND gates here, when they get the signal, it can produce the output theoretically at the same time. Or you can say that they work in parallel. But the output of the OR gate has to wait for the output from an AND gate. That is why we call this kind of circuit two-level AND OR. And from your basic knowledge about digital system, you know that you can put the NOT here, you can put the NOT here and NOT there, you can put some more NOT to get the same kind of signal, right? We have NOT and NOT, and then NOT and NOT, NOT and NOT. So the logic of the system is still the same. Why I put the NOT gate here? Just because if I put the NOT there, here is not the AND gate anymore. This one is, we call it NAND gate. We call it NAND gate. And this one is also not of OR gate. What is it? It's also NAND gate. So two-level AND OR circuit, you can call two-level NAND circuit. Okay, you can prove it by yourself. This one is also NAND gate. And when you go back to review the background on digital system, you will know that NAND gate is one of the fastest circuit in digital circuit. Basically, most of the time we implement the digital circuit by using NAND gate, not AND, not OR. Okay, come back to our analysis here. Because one bit ripple adder is the two-level AND OR. It means that we need two gate delay, one for AND gate, one for OR gate. And because all three AND gates, they work at the same time, or we can say it works in parallel. So in the first level of the circuit, AND gate can take only one gate delay. And the second level, it takes another gate delay. So in total, for one bit adder, it takes two gate delays. So if we have the 16-bit ripple adder, we will have 32-bit gate delay for this adder. This is a very simple performance analysis of a ripple adder. So the question here, how about a 32-bit ripple adder? How much the gate delay for this circuit? It's very simple calculation. 32 by 2, 64 gate delay. If one gate delay means 10 nanosecond, I assume that one gate delay is 10 nanosecond. This is 640 nanosecond gate delay. And what does it mean here? If you remember, at the very first class that we discussed about the computer performance, I asked you about why don't we be 128-bit CPU? If you remember, I asked you why don't we go for the larger data size processor? We stop at 64-bit CPU, and we stop there for quite long time, right? For many years. This is a kind of reason that why we stop here, because if we have the bigger data size, we may have the longer or bigger gate delay or simply slower circuit. That is one of the reasons. But the question here, how can we improve this? How can we make it faster? Any idea? How to make it faster? Because the gate delay here is from the critical part, and the critical path is the carry. So if we improve the circuit in carry, we will get the better circuit. Look at this. Here is, we call it the carry lookalike adder. Look at the simple concept here. We have C1 like this. This is the equation to calculate C1, and here is C2. What happened here? You notice that we can calculate C1 without waiting at all, because all the input here or the parameter here in C1 is they are input. B0, C0, they are input. A0, C0, A0, B0, all of them are inputs from the circuit. So C1 can be immediately calculated. We don't have to wait. But how about C2? C2 have to wait for C1 after calculating C1, then we can calculate C2. But actually, in the real circuit, in the real hardware, the signal go through and it does not wait. But we will get the correct result only when C1 is completed. That means C2 change over time until we get the C1, so that we can get the correct C2. But if we don't want to wait for C1, how can we do that? We use the same idea as C1. C1 does not have any. C1 has only the input. We can change C2, this statement for C2 here, to have only the input. We can do that. How? We just put C1 into C2, and all the terms here will be the input only. So we put C1 here, all the terms here, into this and that. So we will get this one. And look at this equation. You can see that A1, A0, B0, all the terms here are the input. So in this equation, we can calculate it immediately without waiting at all. The question here is, what about C3? Okay. If you go back to the previous slide, you notice that C3 is equal to B2, C2, or A2, C2, or A2, B2. How can you get C3 with the same technique here? We can replace C2 in this equation with this term. When you finish doing that, you will get the equation for C3 that has only input, no weighting at all. May I ask you for C4? Let's spend your time for a few minutes here to do the C4. What is the equation for C4? Let's say let's spend about 5 minutes to do the C4, and you will get the appreciation of the next technique that we are going to discuss. But first of all, you have to do it by hand. Let's try. How long is your equation? Is that longer than 3 lines? You have to start with C3 first, and then you can see what the C4 is. Okay. Anyone from WebEx want to share your answer? You guys are very quiet today. At least you can say good morning. Okay, have a look here. We have C3 like this, and the equation is for C3 is B2 and C2, or A2 and C2, or A2 and B2. So we can insert the third equation here into C3. So instead of instead of having C2 here, we have the whole thing, all the terms here. We put it there and there. So your equation for C3 should be a very big one. Should be very long. And then again, C4 is something like this. We have B3 and C3 and so on. We have C3 here and C3 there. So we just put all the terms here into C3 and there. You will get C4. So the answer for C4 should be very long statement, very long equations. And for me, I'm too lazy. And I believe that some of you may be thinking the same, or I'm too lazy to come up with this kind of solution. Can we get the better one? Can we get the better approach to get C4? From the equation like this, you know that if there are so many terms here, there are lots of AND gates and OR gates. What does it mean? To calculate the C4, what does it mean if you have the really long equation? Yeah, it's going to be very expensive because we need more devices, we need more gates, we need more connections. So it's going to be more expensive than the Lipo adder that we discussed. But here we know that this kind of circuit is faster, expensive though. Okay. Look at this kind of approach. How can we come up with this the simplified equation for the carry? Look at this. We have C1, we have C2, the same as previously. And then we put C2. We put C1 in the equation of C2 and we get something like this. This is the equation for C2. But we can rearrange the terms here into this kind of term. You notice that we have and we have or, and then we have and then we have or. When we notice something like this, we create a new term and we call it the propagate and the generate. So instead of representing the equation like this, we will create a new term. We call P and G for generate, and P for propagate, and GI is equal to AI and PI. PI equal to AI or BI. And with this kind of terms, we can represent the previous equation by using this. If we would like to get a C1, we can get a C1 from G0, P0, and C0. And C2 is something like this. G1, P1, and G0, P1, P0, C0, and so on. So you can see the pattern here. This is the simplified terms of the same equation that I just asked. And you can notice that this one is much shorter, right? This is much shorter. When you see the notation like this, may I ask for C8? Can you do the C8 right now? Previously, I think that if I asked you in a minute before, and I asked you about C8, you will say, oh, impossible to write the equation. It's too long. But now for this kind of notation, if you have the term for propagate and the term G for generate, and we have this form of equation, I believe that you can come up with C8. What is the C8 for now? So can you help me to come up with the solution for C8? G7 or
P7,
P
6,
and
G6,
G6. And then
P7, P6, and G5.
G5. And next,
P7, P6, P5, and G4.
wow, I think all of you can do this, right? P7, and what is next? P6, P5, and then
P4,
P4,
and G3.
P3. And what is the next one? P7,
P7,
P6,
P6, P5, P4, P3, and G2.
G2, P7, P6, P5, P4, P3, P2, and what is next? G1, right?
Yeah.
And the next term is P7, P6, P5, P4, P3, P2,
G1 and G0.
okay, end up G0, no space here anymore. And the last one,
P7 to P0 and then C0.
and then C0. Okay, excellent. Thank you very much. That is the DC8. And from this kind of equation, you can notice that all the terms here, we can do it for C8. And all the terms here are just the input. We don't have to wait for the propagation. And this kind of equation, we call it the Cayley look-ahead adder. How 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 is your feeling? Is that better, or still worse, or still bad, or it's worse than before?
I think it's better than like last one.
Right, I think so. How about you? Right, yeah, and it's kind of predictable. You can write CH without very deep thinking. You can look at the pattern here, and you can come up with the CH. And definitely, you can be asked for C16, but it's too long for now. No, no more. CH is enough. Okay, but in reality, C16, C32, it's possible. But you may notice that we will have the very big circuit for those kind of things. But at least with the Kelly look-ahead adder, now we don't have to wait for the propagation, or we can simply say that the circuit will have the shorter gate delay. But what is the gate delay for the Kelly look-ahead adder? We know that it should be faster because we have the better equation. We don't have to wait. Let's say in terms of C8 don't have to wait for, it does not have to wait for C7. But the question is, what is the performance of this kind of circuit? How can we analyze the performance of this system? How much is faster than the previous one? Look at this. I will go back to this slide later. Okay, maybe this is not. Before we go into the more complex system, how can we analyze the performance of this kind of equation? If you have C4 like this, how much the gate delay it has? Is this the two-level AND/OR circuit? It is, right? I say that it is the two-level AND/OR? This the term that I underline are the AND, and all the AND here, we all them all together, and then we get C4. Agree with me? So this one is the two-level AND/OR. So two-level AND/OR, so we have two gate delay for two-level AND/OR. What else that we have to add into the gate delay? How can we get the G terms? How much? We just need the AND gate, right? So it's one gate delay for AND gate. One gate delay. And how about the P terms? Also one gate delay. So how much in total? 4. Any other answer? Do we have to wait between P and G, or they can simultaneously do the thing together at the same time? It can work as in parallel, right? They can work in parallel. So P and G can work in parallel, so we don't have to add 1 and 1, because this gate delay, they run at the same time. So in total, we need only 3 gate delays for this kind of equation. If you have CH like this, we use only 3 gate delays. How much it's faster than the LiPo adder in case of 8-bit adder. In LiPo adder, if you have 8-bit adder, we need 16 gate delay, but here we use only 3 gate delays. So this kind of adder is 5 times faster than the previous version that we discussed. This is the example of the faster circuit. And you notice that the faster circuit comes with the more expensive devices. They use more gates. And that is why when you look at the modern processor, most of the manufacturers claim that they put more gates in their devices. This is the reason why more gates are better. Okay, when they have more gates, meaning that they have a more complicated circuit, and hopefully they should be a little bit faster or hugely faster. It depends on the circuit that they're working on. In this case, let's say if you have 8-bit adder, Galilee-Lucahen adder is up five times faster than the LiPo adder. Okay. The next question is, you notice that here is C8. It's quite complicated now. What happens if we ask for C16? And what happens if I ask you for C32? You say bye-bye. No. Please, teacher, please don't ask me like that. right? How can we have this simplified version or uh, the better uh, or the trade-off between the faster circuit and the complexity of the circuit? Look at the thing like this. If we would like to build a 16-bit adder, we can we can create something like this. If this box is a Kali lookalike adder, it's a 4-bit Kali lookalike adder, and definitely we will get a C4 here, right? And then we have 4 bits of a result from R0 to R3, and we put A 4-bit and B 4-bit as well. We can have something like this, 4 boxes. This is how we put them all together in the Ripple adder fashion. Because you notice that I put C4 as a C-in of the next bit. So I get C8 here. And then I can have C12 here as the input of the next one. And finally, I can get C16. If I have the circuit like this, what is the gate delay for this kind of circuit? This one has a 3 gate delay. This one has 3, 3, and 3. Because C8 has to wait for C4. And C12 has to wait for C8. And that's in the same fashion, C16 has to wait for C12. So the total gate delay for this kind of circuit is 12. Still, this one is better than the 16-bit Ripple adder, because 16-bit Ripple adder, it has 16 by 2 equal to 32 gate delays. But you notice that instead of 5 times faster, but this time is only less than 3 times faster. So when the number of bits, when you have more number of bits, the advantage of Kali lookalike adder can be reduced from 5 to less than 3. If we put the Kali lookalike adder in the same way as the Ripple adder, we have 4-bit Kali lookalike adder. Again, we have 4-bit Kali lookalike adder, and so on. This is how we put the Kali lookalike adder in the same way as the Ripple adder. How can we improve this? Yes, we can do something in parallel. For example, how can we calculate C4 in advance? How can we get C8 without waiting for C4? How can we get C12 without waiting for C8? How can we get C16 without waiting for C12? And we can use the same technique as what we have done in 4-bit Kali lookalike adder. We can do something like this. Instead of feeding C4 from the first Kali lookalike adder to the next one, we can calculate P0 and G0, and then we can feed them to the second level Kali lookalike adder. So we have a 4-bit Kali lookalike adder like this. This is one box here. Is a 4-bit Kali lookalike adder. Another one, and another one. So we have 4 boxes of 4-bit Kelly lowercase adder. But instead of connecting them directly, the same way as we did with the Lippo adder, we have the second level Kelly lowercase adder like this. And how can we build this box? Look at this one. We can calculate P0, P1, P2, and P3 like this. This is the equation for P0, P1, P2, and P3. And we can calculate G0, G1, G2, and G3. And you notice that G0, G1, G2, and G3, they are in the same manner as C0, C1, C2, and C3 that we previously did. The same pattern, almost the same pattern, right? So when we get P0 to P3, we get G0 to G3, and then finally we can get the second level of the Kelly lowercase adder, and we can get capital C1, capital C2, capital C3, and finally capital C4. And you notice that the patterns of C1, C2, and C3 are the same as what we have done before. The patterns are the same. And with this, you see that this one is quite complicated. The question is, what is going on here? What is the performance of this kind of circuit? This circuit is much more complex than what we discussed. But how about the gate delay here? When we have the more complex circuit, what we have to ask ourselves is the performance. What we gain from this kind of complexity. This is the analysis, the simple one. Because from the equation of C4, the capital C4 is again two-level AND OR, right? It's a two-level AND OR. In two-level AND OR, what it takes two gate delay, and because Pi and Gi are one gate delay as we discussed, so in total, the circuit takes only 5 gate delays for 16-bit Kelly lowercase adder, instead of a 12 gate delay. In the previous slide, we discussed about this, right? This one is 12 gate delay. If we have 4-bit Kelly lowercase adder, 4 of them connected the same way as we did in Lippo adder, and then we analyze, we know that it takes 12 gate delay. But when we apply the second level Kelly lowercase adder, now instead of 12 gate delay, the gate delay goes down to only 5 gate delay. So this one is almost 2.5 times faster than this one. And this is the advanced adder. If you would like to look through the proof of this kind of equation, you can go through the internet. You can see the publication. There are some proof of this kind of equation if you would like to see the details. But I'm afraid that it's one equation, but if you would like to prove it, it takes maybe 2 pages for you to derive the result. So if you have time, please go through. But in terms of Kelly lowercase adder an equation, why do I have to ask an equation? It's just because tomorrow we are going to implement the Kelly lookahead adder. So if you have questions, please ask straight away. Tomorrow we are going to simulate the Kelly lookahead adder. Is that too fast? Because most of the complexity, I just skip it. For example, the analogy to the plumbing system. Do you want me to go through the plumbing system, the analogy? Or please skip it. Don't make me confused. If you want to look at this a little bit, that is fine.
I think it's okay to like for you to go on it ค่ะ
Okay. To go on means skip it, right?
No, I mean like you can teach that about that ค่ะ
Okay. Oh, look at this one. The analogy, what is the analogy here? Look at the P0 here. If you look at the equation, P0 is something like this. P3 and P2 and P1 and P0. What does it mean? If this is the tube, and we have a water gate, this is the gate, can close and open. How can, if we have the water going in to this tube, how can we get the water out here? We will get the water out here if and only if all the gates here are open, right? If we have the gate here, let's say P0 is a gate, P1, P2, and P3, they are the gates. We open the gate so that the water can propagate from this point to this point. It is the same here, right? P0 must be 1, P1 must be 1, P2 must be 1, as well as P3 must be 1. Otherwise, P0 will be 0. All the P's here must be 1. Or simply, if you look at the plumbing system here, all the gates here must be open. If one of them closed, or if one of them is 0, P0 will be 0. This is why we call this term propagate. We have to propagate it from this point to this, and that. Why we call this term generate? Look at this kind of plumbing system. We have the water in G3. If G3 is 1, what does it mean? It can generate the G0 as 1 without looking at the rest of the system. Right? No matter what the values of P3, P2, or P1, or G2, G1, and G0, if we have G3 as 1, we can get G0 as 1 immediately. This is why we call G3 as the generate, because it can generate this value by itself. It does not have to wait for anything else. The same thing here, G2, but G2 has to wait for P3 because we have G2 and P3. Altogether, if we have G2 as 1, P3 as 1 as well, we can generate the G0. And this is the term P3 and G2. And how about this one? If you would like to get G0 as 1 from this term, we must have G1 as 1, P2, and P3. So this is for the term P3 and P2 and G1. And when you look at the next slide, you will notice that the terms here and there are in the equation of G0. This and that. This is the analogy between this kind of circuit and the plumbing system. I believe that today's topic is quite heavy. Okay. Any question? Okay.
I guess so,ค่ะ, but I have to like repeat it myself again.
Yeah, it might take a little bit of time to have a review because I don't want to spend too much time on how to get this kind of equation. But tomorrow we are going to build this kind of system, so you may have to come back to this kind of slides again to look at what is going on, what are the gates that you want to put in the circuit. Okay. Anyway, we will come back to this one tomorrow. We will build 4-bit. Can we look ahead at it tomorrow? And then if you would like to build a 16-bit, we will do something like this. Okay, we will do something like this, not this one. This one is maybe you need a month to complete this assignment. I just kidding. Actually, it is not that very long. If you spend time on it, maybe you can spend let's say 2 full days on this kind of circuit, and you will finish. But I know that student life is not just doing the assignment. You have something else to do? Okay, next topic is the binary multiplication. Maybe we can finish one algorithm and then we will have a break. Okay, let's look at the simple binary multiplication algorithm here. This is what we have. Let's say the example here. We have the multiplicand and multiplier. We have A and B. We can do it by hand. This is quite obvious. When we have 1 by 1001, we get 1001 there. Next, we go to the next bit, which is 0. 0 multiplied to anything, we get all zeros. Next is 1. 1 times 1001, we get 1001. And the last bit is 0. 0 multiplied the multiplicand, we get all zeros here. And then we sum them up, and finally we get this kind of result. This is quite simple, right? This is what we usually done by hand. If you would like to implement this kind of algorithm in hardware, how can we do that? Hey, to do it in software is quite easy. To do it by hand is very simple, and I believe that everyone can do it. But how can you translate it into hardware? If you have something like this is the algorithm that we can use. First, we have to test the multiplier at the bit 0. Multiplier 0 here means the bit 0 of the multiplier. What does it mean, bit 0? If you have 4 bits, in this case, we have 4 bits. This is multiplier 0, bit 0. The rightmost bit. We test it whether it's 1 or 0. If it is 0, we just skip the first step. We can go to the second step. But if it is 1, what we are going to do, in step 1a, we just add the multiplicand to the product or the result. We add the multiplicand to the result, to the product, and place the result in the product register. Next, what is the next step here? We shift the multiplicand register left 1 bit and shift the multiplier register right 1 bit. Why do we have to shift right the multiplier? Because let's say if you have 0, 1, 0, 1 here, this is the same as this one, right? The first time we use this bit, but the next time we want not this bit anymore, we want this bit. But instead of moving this pointer, we move the data. Because you have to think about the hardware. In hardware, we simply use the wire. When we use the wire, we just tap the signal from the hardware, and we just tap it out, and that's it. So it is hard to move the hardware, but it's easier to move the data. So we move the data. How can we move the data? We just shift it right. So this bit have to shift to the right. That is why we shift the multiplier register to the right. And then we repeat this cycle again and again until we finish. In case of 32 bits, we repeat it 32 times. In case of 8 bits, we do this loop 8 times. Okay, this example is quite basic one. Look at the example here. If we represent all the algorithm by using the table, we have this step like this. Let's say if we have the unsigned extension to A and we initialize the register R, A is the multiplicand and B is the multiplier, and R is the product. In the algorithm, we have to check multiplier 0. In this case, we have to check B0 whether it is 0 or 1. So the first time is 1. So we have to add A to R. That is why we get R like this. Because at the very beginning, R is 0. We add A to R, so we get R like this. And then we shift A to the left, shift B to the right, and then this is the first loop. And the next round, we have to check B0 again. And this time B0 is 0, so we do nothing. We skip step number 1. We go to step number 2 and number 3. So we shift left A and shift right B. When we finish shifting left A and shifting right B, so we finish the second round. In the third round, we test the B0 again. And at this time, B0 is 1. When B0 is 1, we have to add A to R. And this is the result that we add A to R. This is step 1A. And in step 2 and 3, we shift left A and shift right B. And this is the third round. When we start the fourth round, we have to test B0 again. And in this case, B0 is 0, so we do nothing. We don't have to add A to R. And then we shift left A and shift right B. And here is the final result. What happened here? This is the very simple multiplication algorithm if you would like to implement it in hardware. And what does it mean here? We have the multiplicand, which is 4-bit, and multiplier, again 4-bit. They are 4 bits long, but in algorithm we need the multiplicand register double size of the multiplicand. If we have 4-bit multiplicand, we need the multiplicand register 8-bit. We need 8-bit for it. But for the multiplier, we need only 4-bit, the same size as the multiplier here. How about the product register? The product register must be double size of the original data. And how about what else do we need to get this kind of result? We need adder. And what is the size of adder? Why we need adder? We have to add multiplicand to the product registers, right? We need adders. And what is the size of the adder? It's the same as the result, which is 2 times of the original data. If in this case, the original data has 4 bits, the adder must be 8-bit adder. So here is the conclusion of what we just discussed. In case of 32-bit data, if you would like to do the multiplication, we need the 64-bit ALU or 64-bit adder, and we also need the 64-bit registers. But the data itself is just only 32-bit. Not including the control circuit. We need the control circuit here. This is how we implement the multiplication in hardware. Is this as simple as what we think? This one is not quite good, right? Because we using the 32-bit data, but we need the 64-bit ALU. And we also need the 64-bit registers to get the multiplicand and store the result. This is not quite good. We will take a break for 15 minutes, and then we will come back for the second algorithms. But before coming back for the second and third algorithms, is that better to have the presentation first? Or you think that should we finish the algorithms and then presentation later. Okay, all right. Okay, take a break now for 15 minutes and then come back. Okay, we are going to continue our discussion on the multiplication algorithm. The next one is the second algorithm. Look at the improved version of the multiplication algorithm here. Previously, we have, let's say if we have the 32-bit data, we need the 64-bit register to handle the data. For example, we need the 64-bit register for the multiplicand and the product. And we also need the 64-bit ALU to do the addition. How can we improve that kind of algorithms? Look at this one. Instead of checking the multiplier, look at this one. We test the product 0. The product 0 means the rightmost bit of the product. Or we can simply call the least significant bit. Test it whether it's 0 or 1. If it is 0, do nothing. Just go to the step number 2. But if the product 0 is 1, we do the step 1a. What is this step 1a? We add multiplicand to the left half of product and place the result in the left half of the product register. What this statement guides us. The product register should be 2 times or double size of the data that we are using. And how about the ALU? Do we still need the double size ALU, or we need just the normal size ALU? The normal size ALU means the same size as the size of data. We just started, okay? We just started. Look at the second algorithm here. Here we just discussed that instead of using the multiplier 0, now we look at the product 0, the least significant bit of the product, and we test it whether it's 1 or 0. If it is 1, we do step 1a. If it is 0, we skip step 1. We go to step 2. But here, in step 1a, we add multiplicand to the left half of the product and place the result into the left half of the product register. I just asking what does it mean here? The size of the product should be double size of the data, and same as before. And how about the size of ALU? Do we still need the double size ALU, or we just use the normal size, the same size as the data? You look at this one. We add the multiplicand to the left half of product. It suggests us that the other or the ALU must be the same size as the data. We don't need the double size ALU anymore. In case of 32-bit calculation, ALU can be only 32-bit ALU. We don't need 64-bit ALU anymore. And how about in step number 2? Shift the product register right 1 bit And now you notice that we have only two steps, step 1 and step 2. But in step 1 can have step 1A, or maybe we can skip step 1A depending on the product zero, whether it's 1 like this or 0. And we repeat the loop in case of a 32-bit calculation. We repeat this loop 32 times. And you notice that this algorithm, we have only two main steps, not the same as previous one. In the previous algorithm, we need 3 steps, right? So this one is shorter, and we can implement it with a better circuit as well. Look at how can we use this kind of algorithm in terms of table. Look at this table. The same as before, we have the multiplicand like this and multiplier like that. In the first iteration, or we can say that this is the initialization, we have the multiplicand like this. So we just simply put the multiplier into the right side of the product. It is not the same as the previous example. The previous algorithm, we have another register for the multiplier, and we must shift right the multiplier register. But this time we just put the multiplier into the right half of the product register. In iteration 1, in loop number 1, we test the product zero, whether it's 0 or not, or 1. In this step is 0, so no operation. So we just skip step 1A, we go to step 2. Step 2, we just shift right the product. And here we get the result from shifting right. Next, we do again, checking the product zero, and at this time it's 1. When it is 1, we have to add the left half of the product with the multiplicand. So this is the left half of the product plus the multiplicand, and we put it into the left half of the product so that we get this one. 0, 0, 0 plus 0, 0, 1, 0. And this is the result. And we put the result into the left half of the product. And then in step 2, we just shift right the product. So this is what we get. Again, in the third round, we check the product zero, and this time it's 1 again. So we add the left half of the product, which is 0, 0, 0, 1. This time it's 0, 0, 0, 1. We add this value with the 0, 0, 1, 0. And here is the result. And we put the result to the left half of the product. And in step 2, we just shift right this value so that we get this one. The last round, we check the product zero, and at this time product zero is 0, so we do nothing, no operation. We get the same as the previous row. And step 2, we have to shift right this one, so we get this one. This is this second multiplication algorithm. If we discussing about the how to be implemented in hardware, it will be something like this. We will have the multiplicand register, which can be at this time 32-bit, not 64-bit anymore. And ALU, again, we can reduce from 64-bit ALU to 32-bit ALU. And as we just discussed in the previous topic, the bigger ALU tend to run slower than the smaller ALU. So it's nice to have a smaller ALU. But the product itself still, we need 64-bit product register. And here is a note that we have to put the multiplier on the right-hand side of the product at the very beginning. This is the implementation of the multiplication algorithm in hardware. And most of the ALU have to implement something like this. There are some limitations of this algorithm. This algorithm is the unsigned operation. This algorithm is the unsigned operation. Why I say it's unsigned operation? Yeah, it's only work on the unsigned integers. But why I say it unsigned only? You can go back to the algorithm, and you may notice that this is the shift right. What happened to shift right here? Yeah, when we shift right something, let's say if this one is 0, when we shift right, we have to add 1 bit in the left-hand side or in the MSB, right? In the most significant bit, we have to add something there. How can we add something there? In this algorithm, we just add 0. We don't have to think about the sign bits at all. So that is why this algorithm is working on the unsigned multiplication only. So you can guess what is the next algorithm should be for. Because this one is, the second algorithm here is just for the unsigned multiplication. If we would like to do this signed multiplication, we have to use the next algorithm, which is this one. This is the third algorithm, or we can call it Booth algorithm. There are 4 steps here. First, we start from step 0, initialization. We have to put the multiplier to the right-hand side of the product. But we need one more flag, or we need one more bit. We call it extra shift. And in initialization, we initialize it with 0. This is the extra bit. Instead of checking only 1 bit of the product 0, this time we have the extra shift. So we have to check 2 bits, which are product 0 and shift. We have to check it whether it's 0, 0, or 0, 1, or 1, 0, or 1, 1. If product 0 and shift, extra shift, are 0, 0, or 1, 1 in this case, we can say that this else means 1, 1. No operation. We don't have to do anything. We can skip step 1. We can do step 2 immediately. But if product 0 and extra shift is 0, 1, not Siri, 0, 1. My iPad would like to talk with me. If the product 0 and extra chip is 0, 1, we have to add the multiplicand to the left half of the product. This is the same as the previous algorithm, right? But the difference is here. When the product 0 and the extra chip become 1, 0, instead of adding the multiplication to the product, at this time we have to subtract the multiplicand from the left half of the product. So we have add here and subtract here. How can we remember this? It's quite easy, right? Because 0, 1, you can notice that this starts from 0. This is a positive value. But this one start with 1 is the negative value. So when it starts with the positive, you add the multiplicand to the left half of the product. But when the product 0 and the extra chip become 1, 0, you have to subtract them. That is the first step. The second step and the third step are almost the same as the previous algorithm. The second step, we just shift right the product, but the shift right here is the sign extension shift right. You have to know that the shifting right here is the sign extension shift right. So you have to look at the most significant bit. When you add one more bit in, you have to add the same value as the previous most significant bit. If it is 1, you have to add 1. If it is 0, you have to add 0. But look at this step 3 here. Because we use the shift right in the product, most of the time when we shift right, let's say if we have 4 bits, like this one is P0, P1, P2, P3, and so on. If you have more bits, when we shift right, P0 will be discarded, right? But instead of discarding this number or this bit, we put P0 into the extra shift. We just update the extra shift by using the value of P0. Or you can say that P0 extra shift is the next bit to P0. You can say something like that. Okay, and then we repeat step 1, 2, 3 until we go through all the bits. If we have 32-bit data, we have to run this loop 32 times. Step 1, 2, and 3. Let's see the example here. The example in this slide is the same as that in the previous algorithm. We have 0, 0, 1, 0 times 0, 1, 1, 0. So in the initialization, we have the multiplicand here, 0, 0, 1, 0. We initialize the right half of the product by using the multiplier. We put the multiplier to the right-hand side of the product, and we initialize the extra chip with 0. So in the first round, we check the product 0 and the extra chip. In this case, there are 0, 0. So we have no operation. We do nothing. So we just copy the previous value to this row. And then we shift right the product. When we shift right 0 here, go to there. And then we have the result from shifting right is like this. Okay. This 0 go to here. So we can start the second round. And the second round, we can notice that this is 1, 0. What does it mean, 1, 0? We have to subtract the left half of the product with the multiplicand. So we have 0, 0, 0, subtract by 0, 0, 1, 0. How can we subtract them? How can we do this subtraction? What I prefer, I to change it to plus, and I change it to 1, I change it to 0, 1, then 1, and I have the carry in as 1, and I do just the simple add. So what I get is 0, 1, and then 1, 0, and then 1, 0, and then 1. So I just put this one to the left hand side of the product. That is why I got something like this. That is why we got this one. Next, we have to shift right the product. So when we shift right, the number 1 here, go to there, do the extra shift, and the rest go to down here. And you notice that we have to add one more bit into the product. At this time, we add 1 to the product because the MSB here is 1. That is why we add 1 here. This is how we do the sign extension. And we finish the second round. Next is the third round. We have to check the product 0 and the extra shift. At this time is 1, 1. And when there are 1, 1, we do nothing. So no operation here. We just copy this row to this one. And we just do the simple right shift. So the number 1 here, shift to this one. And all the bits from this row go down here. And we have to add 1 to the most significant bit here. Because when we add, we add with design extension, right? The last round, we have to check product 0 and the extra shift, they are 0, 1. So at this time, we have to add, right, 0, 1. We have to add the product with the multiplicand. We have the product 1, 1, 1, and the multiplicand is 0, 0, 1, 0. We add them together. So the carry is 0 when we add. This one we get 1, 0, and then we have 0, 1, 0, 1, 0, 1. That is why we get this, and then we got that one. And the final step, we just shift right the product. So this 0 here, go down here, this bit. And then all the bits here go down here. And the last one we add 0. Why we add 0? Because with design extension, we have 0 here. So that is why we add the 0 there. Any question? Is that too fast? Do you want to try by yourself? We still have, let's say we have time for doing the example by ourselves. Shall we do it? Let's say if we have, again, 4 bits, I think that is enough for us to try on. Let's say if we have the value like this, we have 1101 times 0101. How about this? Can you use the Booth algorithm to come up with the result of this one? Let's try. Let's try. We have 1101 times 0101. What's that? Shall we do it together? Oh, it's unanimous, huh? Oops. Uh-oh. Sorry. When it come back with nothing. I have to start everything again. 1101 times 0101, right? At step 0, we have the multiplicand as 110, and we do the initialization. And our product should be, oops, sorry again. Maybe I need something. Okay. 1101 times 0101. Let's see what will happen again. Init, and I have the product as 000, and we have to put the multiplier to the right hand side of the product. So we put 0101 here, and the extra shift is 0. This is a product, and this is the extra shift. So the next, in step 1, we have to look at the product 0 and the extra shift. Now there are 1 0. So what we are going to do here? We update the product by subtract it from with the multiplicand. Or in this case, we have 0, 0, 0, and we have to subtract it with 1, 1, 0, 1. So I simply change it to plus, and I change to 0, 1, 0, 0, and I put the carry in as 1. Now I can get 1, 1, 0, 0. I get 1 here. I get 1 here, get 0, and get 0. Is that correct? Tell me, just in case I'm wrong. Okay, 0, 0, 1, 1. So I can get 0, 0, 1, 1 and put it on the left-hand side of the product. And for the right-hand side of the product, we just put the same. There's nothing changed. And the extra shift is just the same. This is step 1A. And then we have to shift right the product. Shift right. How can we get the shift right? 1 here, go to the extra shift. So in this case, extra shift is 1. And then 0, 1, 0, 1, 1, 0, 0. And because this bit is 0, we have to add 0 here. This is the first step, the first graph. How about the second round? In the second round, we have to look at the product 0 and the extra shift. In this case, is 0, 1. So what shall we do for the second round? we update the product by adding the product with multiplicand, right? Because this is 0, 1. The product 0 and the shift, extra shift, they are 0, 1. So we have to update the product by adding it with the multiplicand. The product itself is 0, 0, 0, 1, and the multiplicand is 1, 1, 0, 1. So we have to add this one with 1, 1, 0, 1. When we add these two numbers together, what is the result? 1, 1, we get 0, 1, 3, 1, 0, 1, 0, and then 1. And the right-hand side of the product is the same as before. Again, we have to shift right the product. Too lazy to write down the whole word. So when I shift right the product, this 0 go to the extra shift. So I get the 0 in extra shift. And 1, 0, 1, and then 0, and then 1, 1, 1. And what should I put in here? We do design extension shift right. So we put 1 there. So I just put 1 there. And this is the second step. How about the third step? We have to check the product 0 and the extra shift. This one is 1 and this one is 0. So what shall we do next? We update the product with this one, P minus multiplicand. So how can we do that? The product itself is like this, 1, 1, 1, 1, and the multiplicand is 1, 1, 0, 1. We have to subtract the product with the multiplicand. It's the same as before. I change this to 0, change this one to 1, 0, and this one to 0. And the carry should be 1. And I just change to add. 1, 1, 0, I get 0. 1, 1, 1, I get 1 and 1. 1, 1, 0, I get 0. 1, 1, 0, again I get 0. So the result is like this. 0, 0, 1, 0, and then 0, 1, 0, 1, and then 0. And then what is next? Shift right product again. This time I get 1 there because 1 here, go back to there, right? Product 0 go to the extra shift. That's why extra shift was updated to 1. And 0, 1, 0, 0, 1, 0, 0. And what should I add to the most significant bit here? I add 0 because in the sign extension here is 0, so what I add should be 0 here. And this is the third round. How about the fourth round? We have 0 and 1 there. What shall we do next? We update the product by adding the product to the multiplicand, right? Because this one is 0, 1. 0, 1, we do the adding. How can we add 0, 0, 0, 1 to 1, 1, 0, 1? This is the multiplicand. 1, 1, we get 0, 1. 1, 0, 0, we get 1, 0. 0, 0, 1, we get 1, 0. 0, 0, 1, we get 1, 0. And then we get the right-hand side of the product the same as before, like this. And then finally, we should write the product. So we get this 1, 0, 0, 0, 1, 1, 1, and then we put 1 there. Because the sign extension here, this is 1, so we have to put 1 there. And this is the result. I'm not quite sure whether you get the same or not, or you just look at what I'm doing. Just try to verify the result. It may be wrong in some places, so verify the result by yourself, okay? But I just show you the algorithm, how to come up with the result. If I do something wrong in adding or in subtracting, you can correct by yourself. If I ask you something like this in the quiz, is that possible? Something like this. Okay. Yeah. Any question before we finish this chapter? This is how we implement the mathematic algorithm in processor, or we can say that this is how we implement the ALU. And the data representation here is just only the integer, binary integer. You may think that if we would like to extend our knowledge or our algorithm to the floating point representation, the algorithm should be more complex than this one. And this is how the computer works. So how is it? Is clear or still have some problem or questions? Oh, excellent. Any other questions? How about student on the Webex? Any question?
I guess no.
Excellent. Okay. At this time, I would like you to prepare for the presentation. We have 4 students that volunteer to present their solution. Look at this here. Okay. How about this one? Let Kitty Poom and Napat present the first question, the assembly language of the solution for the assignment 2. And Tanwa and Thanapat present the solution on the machine language. You can talk to each other which part you would like to present. Okay? How about that? I give you about 5 minutes. If you're ready, you can share your screen so that all your friends can see what happened. Okay, shall we start at 11:35? How about that?
Okay, for the first question, case my solution, assuming that the initial I is 0, or else we can add it by adding the following line to above the loop.
Okay.
Firstly, we set up the for part by adding condition where if I is less than j, we will set it to 1, or else we will exit the loop. Secondly, we set up the inside of the if by using the same method as the for, and we set up condition where for else, condition 2 is for else
Okay.
if the condition isn't met. Next, we set up where we set up the code where it will be executed if the if condition is correct. Firstly, we add the I together to form the for I, and we load word. The reason that we add to for I is because it's stored in byte and the word is 1 byte or 4 bit. That's why we add it together to for I and load it with the offset of 0 from the load word. We then add it with the h, which is s1. Next part, Napat will be the one who explain.
Okay. Thank you. Tapan is here. He's sitting on my computer. Okay. Do you want to show your face to your friend? A little bit? No. Yes.
No.
Excellent.
โอเคเมื่อกี้ถึงไหนแล้วเนาะwhen
Yeah, the blue line.
when
Blue color.
we finished the first if we'll add 1 to the I and then jump to the loop again because we finished the if condition, the like for first condition, and
This
then
microphone if you like, so that your friend then can hear.
ไม่เป็นไรครับ
But okay, it's up to you.
and for the else from BEQ if T2 is 0, we will jump to condition 2. The second condition will okay. Use the array index I and -1, and then when finish we'll add 1 to I and then jump to the loop again until the loop is done. If the loop is done, I will not when I is equal or more than j, then we'll jump to exit. Yeah, because when BEQ T1 is 0, jump to exit. Yeah.
Okay, thank you very much.
Is everything in color coded for each part?
Yes. That is very nice. And how about yeah, it's very colorful. Yeah. But how about I equal to 0? How can we get I equal to 0?
For the I equal to 0,
Yeah.
at first I initially assumed that I must be 0, but else if we cannot, if I initially isn't 0, we can do that by adding I with 0, and
Okay.
if the I itself isn't 0, we can substitute by subtract
Right.
itself by
Okay.
itself, then we
Mhm.
can get a 0.
Okay. Or
The reason that I added 0 because if the initial value is like blank or null,
mhm.
we will have the value which is 0.
Okay, excellent. And what else? How you ask your friends? What else that how can we initialize the value of I? What else? Your friends suggested that we can have something like what we presented. For example, we can initialize with this as x2 to 0 and assume that x2 is also big and then put it back. Or subtract 2 by 2 and then put it back to 2. Here is on it. What else can we do? Move. What is the command? You do we have the command move? Instruction move. If possible, if you look at the instruction, you can see more instruction set, right? But if what happens if we have only this, only this instruction that we discussed in our class? That if we have only a few instructions set, only a few instructions. This one is the destination, this one is I, right? S3 is 0 and 0. We can add S2 0 0 to initialize S3 and 0 or S0. Excellent, thank you very much. I think this is one of a very good possible solution. We can do something else that, as I said, when you do some programming, you can come up with some kind of different solution. And this is one of the possible one. Thank you very much for you too.
What's the other method that setting I to 0 that you mentioned? I can't hear you very well. Yeah, when you talk to the
I'm sorry. Add
classmate.
S2 0 0.
Add S2 0 0.
Right. Now you have add S2 0. But instead of adding add2 with 0, you can add 0 to 0 and then put it back to S2. So you can add S2 0 0.
So we change this 1 to 0.
Right.
I see.
That is one of the possible solutions. Yes. Any other question? This is quite good. Thank you very much. And who is next? Oh, in the same presentation?
Yes.
Very good. Thank
I
you.
prepared a slide.
Okay. You guys are very good. You talk to each other, right? Good.
Yes.
Excellent. Okay. So now who is the presenter now?
Hello,
Yes.
can you hear me?
Yes, but the voice is very low.
Okay.
If you can, please speak it very loud.
Hear me better?
Your voice is quite small.
Yeah.
Hello.
Yeah. Better now?
Okay, better now. Okay. Sorry. Suddenly my output device just changed it by itself.
Oh,
Okay. Okay. It's fine now. So I will lead the presentation for questions to answer. So first of all, the question asks that assume the label loop is at the address 8000 in memory. What is the MIPS machine code for the following assembly code? So from the previous lesson, we learned that we learned about MIPS assembly tool, and then now to able to communicate with the machine, we need this assembly code to translate into a machine language too. So how do we do that? First of all, let's take a look at the code. We have several lines of code, right? And to able to translate that, we have some standard to do that. So let's get started. The first syntax I would present it to you is the R format, which the syntax is on the right-hand side below. So you need to translate the syntax from the syntax into the binary code, like the add operand. We need to paste a bit of operation rs, rt, rd, shift amount, and function, like you can see the format below, and then change. And this one is operation add, right? From the table on the right hand side, we can see that the operation is 0. So therefore, we need to write 6 bits of 0. So 0, 0, 0, 0, 0, 0. And next, the syntax is rs, which from the syntax, it is S3. And we need to point out at the table what is the number of S3. So you can take a look at the table, right? And then we need to change that into a binary and paste that binary number into 5-bit. And then we keep on going that like this on the way until the end of the format. And the first three lines is the same because it is the same format. So I will assume that we need to keep going like this on the way until the end of the line 3. But the fourth line is different. So next slide, please. Here. On the previous slide, it is an R format, right? But this time, the fourth line is LW, which came from load word. It's required another format to translate the assembly language to able to make a machine understand. And that format we need to translate to is called an I format, which have a different syntax from the previous format, and the syntax and the format is right here on the right hand side. And what's the difference is the format and the syntax, but the way to translate the code or make the machine understand is quite similar and the same. So we take a look at the table, look how many bits we need to put in and translate the number into binary. And yeah, we look at the table and put in the numbers as the same thing as I mentioned. So the next part, I guess Tanwa will take the lead for me.
okay.
So the next part is uh awareness the Viennese. So next slide is add. So we will continue to add the first three lines. Can you hear me?
Yes.
Okay. So the
Nowadays we
last
don't
one.
say good morning. Nowadays we say, do you hear me?
I'm not sure that you can hear me or not
Yes.
because my internet problems
Yeah, our
good
protocol
now.
changed already. Okay.
Thanks. So the last one is jump.
I think we are discussing on B&E.
Oh, sorry, I cannot hear like the presentation because my internet is very bad.
Right. Mm-hmm. Yeah, maybe this is
Okay.
your friends here. Most of your friends here are playing game, right?
Uh, okay. So on the Viennese, there are syntax OP, RS, RT, and immediate. And OP is the operation, so it takes the first 6 bits of the line, and RS is taking the destinations as 5 bit, and RT is another 5 bits of it. And it used to check if the condition is correct. We will redirect to the immediate with taking 16-bit, which is like the location in the memories.
We say program counter. I
Yep.
think. We call it program counter.
Okay. As in the slide, we take the target address and we pass for offset. So we use the offset. Sorry. We use the offset divided by 4 and we get the offset of 2. So we convert into the two binaries and we extend it into 16-bit and then put it into the immediate format on the last 16-bit.
Okay, this is excellent. Everyone understand how to convert the label into the immediate. You understand? You have to understand this because when you run the code, the operating system will handle how to change the label into the final immediate. Okay, this is excellent.
And the next line we use add, which is the same as the first 3 lines. So it pretty much have no problem, but the last one is J format, which is used for jump.
Right.
It's only take to sets so that this is the operations at the first 6-bit and another 26-bit of the immediate,
Mm-hmm.
which okay the immediate is so it is the same as the last immediate. We instead of we just taking where we jump to, okay, the target address as the operation names jump, so we just jump into the target address.
Okay.
Yes.
And what,
We try.
yeah, and what is the value of 26-bit here?
The value of
Yeah.
36-bit. As the question is 8,000,
8,000.
so
All right.
we translate it into like binaries.
But the binary here is not 8,000, right? The binary here should be what value?
8,020s.
1,000.
The value of the 26-bit immediate here should be should be 2000. Why it should be 2000? Because when you talking about the address in the main memory, the unit of the address is in byte. Is in byte. And how about the immediate that we specify in the jump instruction? We specify it in byte or we specify it in word? We use the unit of word, which is 4 bytes. One word is equal to 4 bytes. That is why if you would like to go to the address 8000, we need only 2000 here. Right? So please verify the value of 26-bit here to be 2000. If it is, this is great. All right. Oh, you have the binary calculator. Excellent. This is a very good shortcut for the Model Life student. Okay.
I think that's all.
We need, we have 26 bits or the immediate, and then we shift left 2 times, so we get 28 bit, and then we need four more bits from the program counter. Yeah, we don't have to add, we just bundle them together. We just need the first 4 bits of the program counter and bundle, yeah, the most significant bit, the first 4 bits, and then we just bundle them together to become 32 bit. We don't add, we just grab them all together. Add the significant bit on the left hand side. Yeah. Okay. Yeah, thank you very much. I think the presentation here for all students are very good. Thank you very much for I think you all has discussion before having the presentation here, which is nice. Thank you very much. Any other question for today? All right. Thank you very much, everyone. See you tomorrow.
Thank you for today ค่ะ
ครับ
You